Another way of using chi-square analysis is looking at independence between qualitative categorical variables. Later we'll talk about comparison of quantitative variables, and then we'll look at correlations and make scatter plots. With categorical variables, you can't quite do the same thing, but what you can do is look at the totals in each category and see how they compare to expectations if the two variables are independent of one another. So our expected values in this case are what you would expect if the variables are completely independent. So this will make more sense when we look at a specific example. Here we're looking at handedness, so whether you're right-handed, left-handed, or ambidextrous, versus gender, men and women. And so here we have some totals. So this is our data. This is the observed totals in each of these categories. So there were 934 men who were right-handed, 113 men who were left-handed, 20 men who were ambidextrous. So we have 1,067 total men, 1,170 total women. And so this is our observed data. Now, over here, these have been converted into percentages, so you can see the percentage comparison. So there's 87.5% men were right-handed, 91.5% women were right-handed. So these numbers are different. They don't match. And so we could wonder, does handedness depend on whether you're male or female? Is there some relationship here between these two categorical variables? If they were completely independent, then we would expect these percentages to be the same. And they're not the same. Maybe you would say they're not too different, but the question is always, how different do they need to be before we can really call that a relationship? So we need to run a chi-square test to investigate this. Now, in these cases, tests of independence, what's expected is unknown, right? We don't know, in theory, what these percentages should be. So we don't have a theory for what to expect. But what we can do is estimate the expected total using what's called a pooled proportion. And really, what that means is you take all of the data and you say, well, I don't care whether it's men or women, I just care about the totals. And so I'll pool the data together. So for right-handedness, there were 2,004 total people, so irrespective of gender. So 2,004 total, so 934 plus 1070. So you do that in each of the cases of handedness, and you have that total. And so we look at the proportion of that total to the total number of people. And so you add the men and the women all together, there's 2,237. So in each case, we're taking the total in the handedness category, and we're dividing by the total number of people in the sample. And that's going to give us proportions that we can use as our expected proportions. So in our whole sample, 89.6% of people were right-handed. So we would expect that as our value. So we're sort of using the sample to estimate what we expect. And then we look at the individual categories and see whether or not they actually differ significantly from that expectation. All right, so in each case, we have this proportion, and to get the expected totals in terms of numbers, we take the proportion and we multiply by that number of that category. So 89.6% right-handed. There are a total of 1,067 men. So we multiply 0.896 times 1067, and that means our expectation is that 956 men would have right-handed, or would be right-handed. And so right-handed, the percentage is 89.6%. So we use the same number for women, but we multiply by the number of women in the sample. And so we would expect that 1,048 women in our sample would be right-handed. And so we do that for each of these handednesses, and that gives us our expected values that we can compare then to the observed. So this is the table with all that data in there. So observed expected for men, observed expected for women. And I'm going to switch over to the Excel version of this, which is organized a little bit better. So we have the observed over here and the expected over here. But it's the same data. And now we can run the chi-square test. It's different from the previous example. The previous example we did with jurors and age, we had a column for observed and a column for expected. And now here it's a little more complicated. We have 2 columns for observed, 2 columns for expected, but that's okay. Excel does not care about this, and we can calculate this chi-square test the same. So let me delete and I'll do it again. Equals chi-sq.test, and we put in the actual range and the expected range. So I highlight all of the data here in the actual range, the observed, and then all of the data here in the expected range. And so this part is exactly the same. Once you have the observed totals and the expected totals, you can use the chi-square test function. And we get a p-value of 0.003. Now, if you want to see the calculation done in sort of a step-by-step fashion like we did in the previous example, here is the observed minus expected squared divided by expected, so the calculation of the chi-squared parameter. So in each case, we're taking the observed total, subtracting the expected total. So for men, it's this number minus this number, squaring that, dividing by the expected. And so we have a value for each one, and then we're going to add them all up to get the chi-squared. So just quickly to look at this formula here, B3, so this number minus D3, that's this number, squared, divide by D3 again. So we have this value. And once you have this value, you can go to the lower right corner, drag it down, and that will fill in all these values. And then for the women, because of the way the table's organized, all I have to do is drag it over here, and it will fill in the women's values because the formula will update. When you drag to the right, instead of using this number, it'll use this number. Instead of using this number, it'll use this number, and it all works out. So then you sum all these values up, and you get a chi-square of 11.47. Now for degrees of freedom. In these independence tests, we have essentially 2 categorical variables, and so the number of categories in each one matters. So if we come over here, the calculation for degrees of freedom in a single categorical variable is n minus 1. But when we have 2 categorical variables, gender and handedness, we need to multiply the degrees of freedom for each one. So the total degrees of freedom, for handedness, we have 3 categories, so that's 3 minus 1. And for gender, we're listing 2, so we have 2 minus 1. And so it's 2 times 1, which gives us 2. So 2 degrees of freedom and a chi-squared of 11.5. So in Excel, the chi-square distribution function, I'm using G6, so that's my chi-square value. Degrees of freedom, I put in as 2, and then put in true to get the cumulative distribution function. And remember, this is the left tail probability. The left tail probability is essentially 0.99677. But then we subtract it from 1 to get the p-value, and you'll see that number matches this number because they're giving you the same thing. It's doing the same calculation, but the chi-square test does this work for you, so you don't have to do it. Okay. So bottom line, what did we learn from doing this? The p-value is 0.003, so that is unlikely, right? That's a small probability chance. And so we can reject the null hypothesis and say that these observed differences are unlikely to have occurred by chance alone. Handedness might be depending on gender. So there might be a relationship here between handedness and gender that can be further explored.